Alright, cool. So this is the first question, right? So one of the major topics that you all have to go through is basically Norton's equivalent circuits and Thevenin's equivalent circuit, right? The breakdown for it in some of these steps is fairly straightforward. You just have to remember the things they have to do and then the process they have to do it, okay? So there's the first question here, just mixing up the paragraph and stuff. So the first question is wanted to go through the Norton's equivalent circuit. So the first thing we have to know is like what is the Norton's equivalent circuit. So in both of these types of circuits, the first one for the Norton, you have a current source, and this current source we call IN or I Norton, and the difference is that you have a resistor that is in parallel with the current source, and we call this one RN. Okay. And then the rest of the circuits, these two terminals here, is basically where you will connect your load, okay? Whatever load you have in the system. So how this is derived is in this question here. The purpose of this equivalent circuit is if you have a big circuit, you can just reduce the entire circuit into equivalent resistance and a current source or a voltage source if it's Thevenin, looking into the circuit from those 2 points, right? So it's basically equivalent to where you're looking into the circuit from. So in this question here, finding Norton's equivalent circuit, looking into the circuit from load terminals AB. So that's very important because this will tell you where you're looking into. So if you look at the circuit, RL is your load. So you're looking into the circuit from points A and B, right? So basically this is your eyeball and you're looking into the circuit from it. So the current will flow here, right? So you're looking at it from it. So the first thing you have to do, first thing, is find Rn. That's the first thing most of the time you have to do. And the second thing, if you're doing the Norton equivalent circuits, you have to find IN. This IN is normally called I short circuit, and you'll see why they call it I short circuit once we start to do the questions, okay? So cool. So we know the Norton equivalent circuit. This is basically what we're trying to get. The first we have to get is IN, the second thing, and the first is RN. Okay? So let's go through the steps to get RN. So the first thing we have to do to get RN is remove the load resistor. So this will be removed from the circuit and you'll just redraw the circuit with some changes. So the first thing I do is remove this. So this goes. So all this branch here, it's no longer any circuit. So you'll basically have two terminals here. So you have a A terminal here and you have a B terminal here, right? So in order to get the RN, the first thing you must do is turn off all of your independent sources. Key point, independent sources. I don't think you all did any questions with dependent sources. So all the independent sources, those sources are the current source. So this is a independent source here, and this is an independent voltage source here. So to turn off a voltage source, you short circuit it, and to turn off a current source, you open circuit it. Basically, just remove it from the circuit, okay? So that is the first thing you have to do to get RN. So that's the first thing we're trying to do. RN and RTH, when we get to the Thevenin, is the same steps, right? There's just an equivalent resistance. So to turn this off, we open circuit it. So we no longer there any circuit, so basically a big space. And to turn off the voltage source, we short circuit it. So that's be replaced with a wire basically. And we then redraw the circuit. So we draw the circuit, the 5 ohm was here. And we keep going, we have this junction here. So if you look at it, right, this branch here, it have no current flowing here because this piece open circuited. This whole branch here, open circuited. Because this piece here is no longer there. So they have a big break in the circuit. So if you have a break in the circuit, no current gone flow, right? So you do really have to draw this entire branch in the reduction, right? So when you go here, you're just going up through the 3 ohm on top here, and then you're coming back down through this 2 ohm here. When we reach here, and it just goes straight back to B. Yeah, so this will basically be your circuit, right? So from there now, the next thing we have to do is basically like reduce the circuit because you're trying to get one resistance, right? So we're trying to break this all into a parallel series, however it is. So the easiest way to do that, so I'll show you a little trick. It's called nodal analysis based on resistances, right? So we know this is our A, which is the input, and we know this entire node here is B. So if anybody confused of what a node is, the simplest way to explain a node is basically a bubble that is bounded between components. So this is a component here, the resistor here, and this is a component here. If I start here, this is just tracing the wire and following it through, and it just bounded by the components. So if I have another component in between here, it will basically break. So example, this is a component here, and this is a component here. So basically the bubble will basically be bounded between these two terminals here. So we know this is B, and well, we could name this one C, right? So the trick is, we know A is the input, quote unquote, we know B is the output, quote unquote, right? And the C is basically in between both of them, right? So what this system helps you is like if you find it hard to know if a resistor in parallel or if it's in series or whatever the case is, you can just use this method. So the first method, you just draw up the nodes and you have your inputs and your outputs, and you just put all the other nodes in one line. So there's a line here, and let's start with this 5 ohm here. So the first question ask yourself is, what two nodes is the 5 ohm in between? So if you look here, there's 5 ohm in between the A and the B nodes. Yeah? So basically that will go between A and B. So this will be a 5 ohm. And you just put a tick in it to let you know that you handled it already. So the next one is the 3 ohm. So the 3 ohm between A and C. A and C nodes, so that'll be right here. So that's done. And this 2 ohm here between C and B, so it'll be right here. And once you finish, you just connect the line segment. So now we can clearly see in this little circuit here that the 3 ohm and the 2 ohm were in series with each other and in parallel with this 5 ohm resistor here. So it makes it easier to see it because it's just in one line instead of it being all over the place in the circuits. So you can do this with any type of circuit. Right? And we just keep reducing. So this 3 and this 2 series each other. So it must be 3 plus 2 is 5. I will in parallel with the 5. We have B and A. So it have two ways. Anytime you have the same resistor in parallel, so the same value in parallel with each other, the equivalent resistor will just be half of one. Any one is the same thing, right? But the long way to do it, anytime you have two resistors in parallel, the total will basically be the product of the two resistors over the sum of the two of them. Oops. So if I do it the first way, both of these basically the same value. So basically be 5 divided by 2, which is 2.5. And if you do it this way, the product, so 5 by 5 is 25. And 25 divided by the sum of them, which is 10, will basically be 2.5. So either way you do it, you'll still end up with 2.5. Right? So remember we were trying to get, so finally we end up with the total resistance is basically 5 divided by 2, which is 2.5 ohms, right? And remember we did all this to get Rn, right? So this is basically Rn, the equivalent resistance looking in from the AB terminals, right? So therefore this RT is Rn, which is equal to the 2.5 ohms, right? This process is the same thing if they ask you for RT, it will be the same process. When you look at the circuits, you look in terms of the terminals they gave you, in this case A and B, you find A and B, check. From there now, you're trying to find the equivalent resistance looking in from those points. So you look into the circuit that they have, and you basically short circuit all the voltage sources, and you open circuit all the current sources. When you do that, majority of the time, the branches that have the current sources in it will just disappear because it's an open circuit. No current will flow there, right? And well, the voltage source will create this replace with a wire. Once you have it in that way, if you get up checking to see if resistors in series and parallel, by all means you could go ahead and get the equivalent resistance. If not, you just try this method. The method is you will have a and B terminals already. Those are known. Inputs and your outputs. So you put your input first, which in this case is A, and your output is B. In between here, depending on how much other nodes you have, in this case you only had one other node, which is C. So the C will be in between, right? So we had next one probably D. Just put it in the middle in sequence, right? So you'll be doing a couple of these, so you'll get the hang of it by the end, right? So that'll be the end of basically finding Rn for RTH. It will be the same steps over and over. You just remove the load. After you remove the load, you look into the AB terminals. You short circuit the voltage sources, open circuit the current sources, redraw the equivalent circuit, and then derive the equivalent resistance looking in from those 2 points. Right? So that's the first piece of the circuit done. So based on what we have on top here, all we just get is Rn, which is 2.5 ohms. The next thing we have to get is In. Yep, so next thing you have to get is In, right? So with In, the two laws that you have to do. The first thing is with In, you have to use the full circuit. So you bring back all the voltage sources and the current sources that were in the circuit from before. Like you have to bring all of those back into the circuit for sure. Okay, if you don't do that, that'll be a problem. Yeah. So once you bring all those back, you basically back to this circuit here. And we have two laws that we normally use. So we have nodal analysis and we have loop analysis. Those are the two analysis methods that we know for this course, right? So when you look at these circuits, we're trying to get I Norton. So to get I Norton, the first thing you have to remember is I Norton is I short circuit, is a short circuit current, right? So to get that short circuit current, wherever the load is, it basically will short circuit that value. Yeah? So basically I want to call it I short circuit. And we'll basically name this I short circuit or ISC for short, right? So this is basically the current that we're trying to find. And the two methods that we have or we could use in order to get that current will be nodal analysis and loop analysis. Those are the two methods that you all know from before, right? So based on what we have here, we're trying to get this current here, which is our short circuit current, right? But if you short this value here, this 5 ohm will also be shorted. So let's have a workaround in which you can actually use the Thevenin in terms of just getting the voltage, and you can actually get the I short circuit. And that simple equation is basically V Thevenin is equal to I Norton by RTH or Rn, basically the same thing. So once you have this value and you have the Thevenin voltage, you could get I Norton by just transposing the equation, right? So some circuits, it's better to just do like that and then convert it back. So you'll try that in this one, right? So now, since we're trying to find the Thevenin, let's go through what the Thevenin is quickly. So the Thevenin is basically the opposite of the Norton. So instead of a current source, we have a voltage source. So we have voltage source, and the name of this voltage source is V Thevenin, right? And is the opposite, so in this case, you have RTH, which is in series with it, not in parallel. Just like before, your load will basically go between the two output terminals. So the calculations for RTH and Rn, remember, is the same thing, right? But this VTH is the other word for it is V open circuit. So basically that's what we want to do in this question. So if we go back to the circuit, So you put everything back like normal, fresh circuit. To get the VTH, instead of short circuiting your load, you just open circuit it, which is why they call it V open circuit, right? So that's no longer there. Yeah, and you're still looking in from terminals A and B for sure, right? Same calculation, you just have an open circuit here. So basically no current flowing in this branch. So we do a nodal analysis. So to do nodal analysis, you just have to follow some steps, right? If you're looking at this, the first thing that we have to do is find our reference, right? Which is basic ground. What I do is I look for most of the bottom node, the biggest one at the bottom. In this case, if you're drawing your nodes first, this entire thing at the bottom here is B. Yeah, remember the node is just bounded between the input components. So you just keep drawing until you encapsulate all the components. So this will be ground. And the voltage for ground is 0. Right? So all this here will be at a potential of 0. Yeah? So that's the first node there. The other node that we have is this node here. So this node is called a GBN node. So what a GBN node is basically this node, the voltage of this node is basically the voltage of the battery, only if the node before the battery is 0, because it will be 0 plus the voltage of the battery. So this will be the G, this will be the B, or this is the N, right? So therefore the voltage of this node here will just be 0 minus our plus is our plus, they're going up, so it'll be 12. So this is our known node, our node that we know the value for, right? Then we have this node on top. Here, which is basically V. So we call this one V. Since we use A and B already, we could use C. Right? And we just keep going. So we don't know what the voltage of this node is. Like we don't know. It's not a GBN node and we don't, it's just two resistors on both sides, which is what it's supposed to be, right? When you draw any nodes for these, the unknown ones, you should have resistors at the ends of it. Right? And then we have the next node here, which is this one, which is the A node. Call this one VA. Okay? And we have VB is 0, okay? So remember, what we're trying to get is Thevenin, which is the open circuit voltage, right? Which is basically voltage in between these 2 points. So if you think about it, once you have the value for VA, since VB is 0, VA will just be Thevenin. So I think someone joined. Yeah. So that's VA, because we're looking for the change in voltage between these 2 points. If this is 0, if this is 5, if we calculate this for 5, VTH would basically just be 5, right? So basically we're looking for VA, which is Thevenin. Yep. So let's go through some nodal analysis. So let's redraw these circuits. Let's look at stats. So we basically have A going up. Right, cool. So this is basically the circuit that we have from before. And let's just draw the nodes and do the calculation first, right? So when you're doing nodal analysis, the first thing you do is you get the reference node. So we know the reference node was this bottom node here. We know this is 0 everywhere. All over here is basically 0, right? And we have this node here, which is 12 because of the polarity of the battery. We have this node on top here, If you don't know what the value for it is, so we call it VC. And we have this node here, which is VA, which is the node that we want the value for. So we basically have two unknown nodes that we want to do basically all the calculations, right? So the first thing you do after you journal the nodes and you have your reference and everything like this node here, a lot of people might think you have to draw this node, but because as I'll explain just now, because what you're looking for is the currents into or out of the nodes, you don't need to do this node here. You're kind of redundant doing this one. You do after doing so, you need to draw this one in, right? So let's continue. So how much unknown nodes we have? We have VA and we have VC. So basically, we need to derive an equation to solve them simultaneously to get the value for VA. Okay, that's basically what we're trying to build up to. So the first thing we do is you assume a current direction. So in this case, I normally assume the current is going out. So just pick one and don't change it, right? So it'll help you with a lot. So whatever you do for one node, you have to do for all, right? So since you're assuming the current direction going out at the end points of the nodes, it will just be good. The currents will be going out. Now this have no current in it, so this will be. You don't need to do it for this node because we already know the voltage for it. We don't need to do it for this one because we already know the voltage for it, right? So that's the first thing we do. The second thing we do, we just have to get the nodal equations and just solve them simultaneously basically. So you'll start with VA. So what we're looking for, you have to remember, right? For nodal, you're looking for currents in and out of the node. You have to remember that, right? You're looking for currents in and out. You're basically using KCL. Yeah. So using KCL, and if you all forget what KCL is, that basically means the sum of the currents going into a node is basically equal to the sum of the currents going out of the node, right? That would be the nodes. So let's start with VA. So we have how much endpoints we have. So we have a little equation for each endpoint, right? And a little kind of thing you could use to remember it is basically where you're coming from minus where you're going to divided by the resistor between it. Yeah. So if we're doing the VA node, we have this endpoint here, we have this endpoint here, and we have this endpoint here. This don't have anything else because it's an open circuit, right? So for VA, we basically will have this one here. So the node we coming from is VA minus the node we go into, so we go into 0, and it divided by the resistor in between it. You must always have a resistor in between it, right? So that's for this endpoint here. Then for this endpoint here, think about it, right? So you're looking for current going out, but you have a current source here already. So basically, you technically know what the current in this branch is. So based on the polarity, since you assume the current going out and he going in the opposite direction, the current for this branch will just be -4. And then up here, same thing, you're coming from VA and you're going to VC. So we're coming from minus, we're going to, and you're divided by the resistor in between it, which is 3. So we have 1, 2, 3 endpoints, and you just make it equal to 0. Yeah, and is a good rule of thumb to simplify it one time. So basically, you multiply everything here by 15 plus multiply everything by 15. So basically, 5 into 15 is 3. So you basically get 3 VA here. Now, that is unit step for this piece here. Then 1 into 15 is 15. 15 by 4. Get 60. I think somebody else. Last person. Alright, cool. Yeah. So then 3 into 15 is 5, so you have to multiply 5 by both of these. So it'll be 5VA and minus 5BC, and you make it equal to 0. Right, now you just simplify, so you just group like terms. So you have 3VA here and 5VA here, so you get 8VA, and then you have no more VCs. And your character is 60, so you get equal to 60. So that'll basically be your first equation. So the first equation. That is for VA. So now just repeat the same process for VC. So it's a different color. Right, so for VC, same concept. So you look, so VC have two endpoints, which is this one here and this one here, and we already assume the current is going out. So you use the same thing that's coming from minus we're going to divided by the resistor in between. So for this one here, we're coming from VC and you go into 12. Because that is the voltage for this node here, right? And you divide it by the resistor in between it. Then you have this endpoint here. So same thing, so it's where you're coming from, plus where you're coming from, minus where you're going to, which is VA. And you divide it by the resistor in between it, which is 3 ohms. And you make it equal to 0. And same concept, you have to simplify it one time. So to simplify this, we just multiply both by 6. So in this case, you'll end up with 3 VC, and then a minus 36. It's 2 into 6 is 3. 3 by this and 3 by this. And then 3 into 6 is 2, so you end up with plus 2 VC minus 2 VA is equal to 0. And simplify. So what we have in common? So we have 3 VC here, and we have 2 VC here, so you get 5 VCs and minus 2 VAs, and your character is 36, and you get 36. So this will be equation 2. So just like normal maths, you basically have two equations and two unknowns. So the amount of unknowns must always match the amount of equations that you have, right? So you could use your calculator to do this, right? So it's actually the easiest way to use your calculator to do this, right? If you have a Casio, most Casios could do simultaneous like this. So in your calculator itself, you end up with a table. So in order to use a calculator, you must write it in a form that the calculator could use. So in this first equation here, so we have 8VA, and we have 0VB, and you have minus 5VC equal to 60. And we have this one here, so you have 0 minus 2VB, so then 0VB, and then plus 5VC, and equal to 36. So if I actually use a calculator, what I'll do, I'll record a video of me using a calculator to do it, and I'll send it in the chat, right? So, but rule of thumb, know how to solve simultaneous equations. So that's more of a maths issue, right? We don't have time to go through how to solve a simultaneous. So what I'll do, I'll send a video in the chat also how to use the Casio to do it. I believe we could do it in the sharp, but some sharps more updated than the others. Alright, but as a rule of thumb, you should know how to solve a simultaneous equation, okay? Anyway, so when you just solve the simultaneous equation, you'll basically get the value that we're looking for. So you have two values. So the value we're looking for is VA, which is the first value. So once you solve it, you'll end up with VA being equal to 16 volts. So just remember the letter that I was looking for is the one you had to solve. Right? Cool, yeah. So yeah, so cool. So we have, so this will basically be beta based on what you was calculating for, right? So that's Thevenin, and all you really need to do, just remember, from here, since we have V Thevenin and we already have iron, we could get iron by just dividing. So you end up with 16 divided by the 2.5 and you'll end up with the 6.4 amps, right? The circuit basically finished. We already have iron, which is the 6.4 amps, and iron was 2.5. Yep, and that's basically the circuit. And actually, from this, you already have two of them already because we just get the V Thevenin already. So if you wanted the Thevenin equivalent circuit, it'll just be the VTH, which is 16, in series with the same 2.5. And with a load will go across. Yeah, that's basically it. So just to recap, so we have two types of circuits right here. So this one here is your Thevenin, and this one here is your Norton. So for the Norton, you need iron and you need Rn. Iron is also called I short circuits. Rn is basically just I equivalent resistance, right? And for the Thevenin, the first thing you need, just like before, you need VTH or V open circuits, and you need RTH. And the equation that basically linking both of these equations or circuits together is basically V Thevenin being equal to I Norton by RTH. And just remember RTH is the same thing as Rn. Yeah? It's the same circuit reduction for both of them. Okay? Cool. So that is basically the Thevenin and the Norton equivalent circuit. So the next things from here that I'll just run through one time. There's something called the maximum power transfer. So can I use the circuits right here? So if that asks us to calculate the maximum power transfer for both circuits, the maximum power transfer occurs when your load resistor, which is basically the resistor will be here for the Norton or across here for the Thevenin, is when that RL is equal to the RTH. So right max power. Right, somebody, I'll leave that as a question. So how you got 4 in the node analysis? 4. When you say 4, which 4 you see in there? There's a real big question. Okay, you're talking about this 4 here? Which you could use your mic and talk in it, it's okay. So I can understand what I'm asking. Which 4 you talking about?
Yeah, so you hear me?
This 4 here?
Yeah, it's that one.
Alright, cool, great. So nice. So remember, with node analysis, you're looking for the currents in and out of the node, right? Remember that? So we have this endpoint here.
Oh, wait, that's 4 arms there.
Yeah, that's
Oh,
4.
I thought it was an H. My bad.
Okay, cool. So you're good there, right?
Yeah, yeah.
Cool, nice. So you can ask your questions. Alright, so back to the maximum power transfer. So you have two equations for the Thevenin. The maximum power transfer, as I said, for both equations or both equivalent circuits, the maximum power transfer occurs when your load resistor is equal to the value of RTH or Rn. This is the same value for both of them, right? That's when the maximum power transfer occurs, right? All you need to do is just plug in the value. So for the Thevenin equivalent circuit, the Pmax is basically a V Thevenin voltage squared divided by 4 RTH. I'll separate them with 4 like that. By 4 RTH. Okay? So then this one on top here, it will be 16 squared divided by 4 by 2.5, right? And then for the Norton, P max would basically be your Norton current squared by Rn divided by 4. Yeah. So in both cases, you'll have the values for both of them already. So you don't have to worry about like pulling stuff out that's in here. You have the values for both of them off the bat. So cool. And that is basically the first one, right? So stopping for question before I do the next question. You all have any questions on this?